Hello, good morning everyone. Welcome to today's chapter, that is triangle similarity and trigonometric ratios. How are these two related? So consider we have two triangles here, that is triangle ABC and triangle DEF, and as we can see in the figure they are right angle triangles, so angle F and C are 90 degrees, and we also know that angle A is equal to angle D. Okay, this is what is given, it is known to us. Okay, now how we can proceed further, I'll tell you. Now, they both have the same angles that measure theta, and they both have 90-degree angles also. So, angle ABC will be congruent to angle A. So, I'm sorry, angle A will be congruent to angle D. This is what the congruency condition is. Okay, because they are same. Next, what do we know about the two triangles now? Because they are two angles which are equal. If we know for any triangle, sum of all the angles is 90 degree, 180 degree, isn't it? So, if these two triangles are known, so one is 90 degree, this is 90 degree. So, what will this be? This angle D plus angle E is equal to 90 degrees, isn't it? Because the sum of all three angles are 180. One is already 90. So D and E will be 90 degree. So we know angle D. So angle E will be 90 minus angle D. So now angle E will be 90 minus theta. So this angle is 90 minus theta. Same way for this also, because angles are similar. So 90 minus theta. Now what do we conclude with this? So if we have two angles in common, we are going to have the third angles also in common. This is the condition for similar triangles. If you know what is similar triangles, this will be the condition, that is angle angle. It is called AA, in which if we know the two angles are similar, then the third angle also will be same. This is called the angle angle condition for similar triangles. So we have concluded that our two triangles will be similar. Then if we have the three angles in common, we are dealing with similar triangles. Now we have already I have already told you what are the angles. Now why is this become interesting? That is because in geometry we know that the ratio of the sides of the similar triangles are also going to be the same. This is what the ratio of the similar triangles will say. That is, I will tell you, S S S. That is a condition. I already spoke about AA condition. That is angle angle. Now for the similarity to exist, there is one more condition known as SSS, which states if two triangles have three pairs of sides in the same ratio, sides of the ratio of the sides in the same ratio, then the triangles are similar. That is, the ratio of this side by this side is equal to this side by this side. Then that is one similarity condition. That is the side ratio. Now I'll write those ratios so that it becomes clear to you. So what happens is, we can initially deal with these two sides. Okay, so let me start by writing the hypotenuse, which is already known to us as AB. Okay, so one more side, we can take any sides. Okay, for example, I will take here um, BC. Okay, let me write BC in the top and hypotenuse in the bottom. So, uh, BC, just take a side of one triangle, that is our ABC, and the hypotenuse AB. Now, this this is the similarity condition. That is, what is the corresponding side for BC here? EF, isn't it? So, EF by ED. This is one condition which we got from this. Okay, now let me write another side which we can write. For example, if we take AC by AB, that will be AC by AB is equal to, what is the similar side of this one? This will be DF, isn't it? That's in the base. So DF by DE. That will be same, ED or DE, hypotenuse. Next, what is remaining? BC, this one, BC by CA, without using the hypotenuse now. BC by CA, that is equal to the standing height one, that is EF by, sorry, uh, EF by DF. Okay, so this is how we have concluded with our similarity condition. Now we got all of this form, the fact that the two triangles are similar. How do we proceed with this? We can give the names to this ratio relative to the angle theta. If we consider the angle theta, these ratios, this ratio and this ratio and this ratio can be named. Now what is that from the theta's point of view? What is theta? This is the angle. This symbol is referred to as theta. Okay, I will tell you what is that. Now, from theta's point of view, we can see that BC by BA. So, BC by BA, that will be theta's point of view. This will be opposite by hypotenuse, isn't it? So, we can write opposite by hypotenuse. Same thing will happen in the another triangle, that is EF by ED. So EF by ED, that is opposite to theta and the hypotenuse of this triangle. So this condition satisfy here as well. Next, AC by AB, that will be AC by AB, that is adjacent to theta and hypotenuse. Same way, DF by DE, DE and the DF. DF is adjacent and DE is the hypotenuse. So we can write here as adjacent side. These two are adjacent sides, and these two are hypotenuse. Next, what about BC and EF? BC, where is it? BC is the opposite side, EF is the opposite side. So we can write the numerator as opposite. And what about CA and DF? We have already written here. CA and DF are the adjacent sides. So adjacent side. So what will all this lead to? The ratio of the opposite to hypotenuse is going to be same for the two triangles because one of its angles are theta, isn't it? So this is how we have concluded. And as the mathematicians call it by definition, this is nothing but our sine theta. What is this? Adjacent by, this is our cos theta, and this is our tangent, tan theta. This is what the mathematicians call it. So this is how we have come from the similarity condition to trigonometric ratios. Let's proceed. I'm going to solve a problem with it. So with the problem here shows that there is a triangle, right angle triangle, and a parallelogram. Parallelogram is named as ABCD, and EFG is our triangle, right angle triangle. It is given that FEG and DCA, that is FEG, DCA and CAB, all these angles is equal to 90 degree. Next, it is also given that, let me change the color, that is E, F and G, then C, B, C, D and A, and C, B and A, all are equal to 31 degrees. This is already given in the question, students. Now they have asked us which of the following is true, whether it is A, B, C or D. Now how do we evaluate this problem is, we have to take each condition and see whether it is coming true for every triangle, every diagram. So let's start. That is first condition we have taken, that is tan ADC is equal to AC by EF, whether this condition is true. Now, we can, as I will write, what is first tan ADC. So, tan of ADC, angle ADC is equal to, what is that tan AD? Where is ADC? A, D, and C. We are going to refer to this space right now, which is that this space. Okay, only this space we are referring. So concentrate on that space. That is ADC is equal to, which is the ADC. So this is our reference angle. So which is what is tan? Tan is nothing but, I have already told this trick in the previous videos. So Ka and Toa. Okay. So Ka Toa. This is A and H. So what is tan? Tan is nothing but opposite by adjacent. So opposite of this 31 is CA. That is AC, whatever. And adjacent of 31 is, this is a hypotenuse. So the adjacent is this side. That is DC. Okay. Now, where is the relation? This is the definition for tan. Okay, that is opposite by adjacent. This is how we have evaluated. Now, here it is, this one is a completely different figure where EF is included. That is EF. Where is EF here? It is in this triangle. Now, if we could find the length other which of the EF, and we could equate somehow to DC, because we have got it as DC. We know there is no relation between EF and DC. So how do we know whether they are same? Because first of all, they are not in the same figure. So how do we know? If we can prove that DC is equal to EF, then we can substitute EF as DC and say that yes, the A condition is correct. But we cannot know, because for God knows this can be of any million meter length, and this can be of some other length. So what, we cannot prove it anyway because of these two figures. So we have to conclude that the first condition is wrong. Okay, now let's move on to the second condition, that is sine CAB is equal to DC by BC. Now what is sine? So okay, SOH, that is sine is equal to opposite by hypotenuse. Sine CBA, now we are concentrating on CBA, this side of the parallelogram, this triangle. Okay, now sine CBA, that is equal to opposite by hypotenuse, that is opposite by hypotenuse, that is sine CBA will be equal to, opposite is CA, then hypotenuse is yeah, it is BC. Okay, now BC is as they have given, so this DC and AC, how we are going to prove that it is equal? There is no evidence given in these two figures that DC will be equal to AC. Okay, this figure is not required here. So is there any way that DC is equal to AC? Is there any way to find out? No, there is no evidence given in the figure, so we cannot equate this and this as equal, and therefore this option also will become wrong for us. So it is obviously not both, so our answer is neither. Okay, so this will be all for today. This is about triangle similarity and the trigonometric ratios. I'll come up with some more videos in the next following videos. If you have any doubts, you can please post it in the comment. It will be really helpful and a good feedback to me. And also you can email me to my Gmail that I will be mentioning in my comment. So thank you. Have a good day and have fun learning.